Hello my dear students, welcome back to the online lecture video series on electromagnetic theory by AVS Deepak. In the previous lecture, we have seen Maxwell's equation for static fields, that is static, electric and magnetic fields. The meaning of static fields, as we have discussed many times, is that they don't change with time. The Maxwell's equations we have seen are that the divergence of electric flux density is the charge concentrated at the point, and the curl of electric field intensity is equals to 0, which means that the electric field intensity is conservative, and divergence of magnetic field intensity is equals to 0, which comes from the fact that magnetic monopoles do not exist, and del cross H bar, the curl of magnetic field intensity, is equals to J bar, comes from Ampere's circuit law. After these four equations, we have also seen Poisson's equations for these static fields. Poisson's equations are defined using the Laplacian operator for scalar electric potential and the Laplacian operator for vector magnetic potential. The Poisson's equations are that the Laplacian of electric potential is given by minus rho v by epsilon, and the Laplacian of vector magnetic potential is equals to minus mu J bar. So these are the Poisson's equations for static fields. When we are discussing about the charge-free regions and current-free regions, these equations get limited to the Laplacian equations for static fields, where the Laplacian of electric potential is equals to 0 and the Laplacian of magnetic vector potential is equals to 0 for charge-free and current-free regions. So these are the concepts we had discussed in the previous lecture. So in the current module, we would start our discussion on time-varying fields. When I say time-varying fields, whether there be electric field or magnetic field, they are changing with time. They are no longer constant. So in today's module, we would discuss Faraday's law, Lenz law, and we'll discuss the amount of induced electric field, and then we would modify the Maxwell's equations for electric fields. So what is Faraday's law and why did it come? So when Einstein has discovered that if a current is passing through a conductor, it would produce a magnetic loop around the conductor, right? This has been identified by Einstein and Weierstrass together. That is, Einstein has given the conceptual and Weierstrass have been quantified. Now Faraday tried to observe if its converse is true. That is, if we have a magnetic field, would it be able to produce current? So that is what he wanted to identify. So what he identified is that if I have a static magnetic field, that is a constant magnetic field, then I am not getting any current out of it. But he has observed that an electromotive force can be induced in a closed circuit, or I may say a closed loop, by varying the flux linked to the loop. That is, you know that electromotive force is the force required to move a body, move an electron or move a charge from one point to another point. So now if I am here in a closed path, now there should not be any energy required in moving an electron from here to here, right? In other words, it would come to the potential difference across a closed path is equals to 0. In other words, integral of E bar dot dl bar should be equals to 0 if it is closed path. But what Faraday has observed is that if I have a closed path, but if there is change in the flux link around this path, then I am getting an potential difference. That is, he started here, he moved in this way, this way, this way. By the time he came here, the electric potential here is different as the electric potential when he has started his movement. Right? That is what I mean by the EMF around a closed path. What he has also observed that is that it is proportional to the rate of change of magnetic flux linkage. If the magnetic flux linkage is psi, is the flux linked to the loop, the change in the magnetic flux linkage is d phi by dt, then he has observed that the induced EMF is proportional to the change in flux linkage. Not just that, if we had this loop is made of multiple turns, if there are multiple turns, if you are making multiple turns using the conductor, now the induced EMF is not just proportional to the rate of flux linkage, but is also proportional to the number of turns the conductor is facing. The induced voltage or potential difference across a closed path was proportional to n times d psi by dt. If we are talking about a single loop, then n would be equals to 1. So therefore, BEMF is proportional to d psi by dt. So this has been observed by Mr. Faraday. Now, if I have an electromotive force, that means it can push the electrons from one terminal to another terminal in a closed path. That means the movement of electrons themselves cause current. So such current which is flowing is called the induced current. So because of the induced EMF, there will be current, and such current is called as induced current. And we have seen from Einstein's experiment that if there is some current, then there is a magnetic field. So because of this induced current which is flowing in a closed path, there would be an induced magnetic field. It has been identified that the magnetic field induced is opposing the flux linkage. That is, if the flux linkage is more, the rate of change in flux linkage is more, then it is resulting in high EMF. Because it is resulting in high EMF, it is resulting in high induced current. Because the strength of the current is high, that means the magnetic field induced is high. And the magnetic field which is induced is opposing the change in flux linked. So this is the observation made, and they have come to a conclusion that VEMF is equals to plus d psi by dt, where the negative sign indicates the opposing force. And it has observed by Lenz, and it is called as Lenz law. The Lenz law says that the induced EMF always is in a direction such that it opposes the change in flux linked. Now, let us discuss if there is any electric field induced because of this. We have already seen that there is a magnetic field which is induced, which is opposing the original flux linkage. Now we would see how would it create an electric field, because we have already seen that an electrostatic field is generated by charges at rest. When we are discussing electrostatic, we have seen that if there are charges at rest, they create an electric field, static electric field. At the same time, we have also seen that the electric field always points to the direction of decrease in electric potential. That is, there is a relationship between electric field and electric potential. So if there is potential, there is bound to be electric field. such potential, such induced EMF would also result in an electric field. Such electric field, which is because of the induced electromotive force, is called as induced electric field. Now, such induced electric field is not conservative. Why is it not conservative? What is the meaning of that? It is not being conservative is, if it is conservative, then the closed path of E bar the DL bar should be equal to 0. That is, potential difference across any closed path should be equals to 0. But we have seen that the closed path, around the closed path, the potential difference is not equals to 0. Instead, it is equals to VEMF. That means the electric field which is induced is not conservative, but instead this is equals to VEMF. But from Lenz law, we have already seen that VEMF is equals to minus d psi by dt. So I can write that the closed path integral of an electric field induced is equals to the change in flux linkage. Of course, for the negative sign, which signifies that it is opposing the direction of change in flux linkage. Now, if you remember Stokes' theorem, it can convert any closed line integral into a surface integral, that it is surface integral of del cross E bar dot E. And when we talk about the flux linkage, you may remember that the relationship between flux linkage and magnetic flux density is such that psi is equals to integral of V bar dot ds bar. Therefore, I can write that integral of E bar dot dl bar is equals to minus d by dt integral of surface integral of magnetic flux density. Now, there are two factors here. One factor which is affecting the flux linkage is obviously the magnetic flux density. And the other factor is the surface itself. So, the variation in time can be because of three factors. One factor is when the loop is constant. That means the surface is constant, but there is change in the magnetic flux density. That is the first condition, or the first way of change in flux. And the second way of obtaining change in flux is the magnetic flux density is constant, but there is change in the loop. That is, the loop is moving. Observe that if I have magnetic field density, magnetic flux intensity, which is pointed in this direction, because it is magnetic field, you know that the magnetic field at one point and the magnetic field at another point are two different entities. So you may very well have a region where the magnetic field intensity is high, and you have another region where the magnetic field intensity is low. Now, if I am here, if my loop is here, then that means because the magnetic flux density is high here, then the magnetic flux which is linked here would be high, whereas if my loop is now here, now because the magnetic field intensity here is low, then the magnetic flux linked will also be low, therefore variation in the flux linkage. Or it may very well possible that the loop is also moving and the magnetic field intensity or the magnetic flux density is also varying. So these are the three scenarios in which there is change in the flux linked to the loop. Let us analyze what would happen in each scenario. So let us first consider what would happen if a stationary loop is in a time varying magnetic field. So it is very obvious, the same expression, that integral of E bar dot dl bar is equals to minus dou by dt surface integral of V bar dot ds bar. But you may identify that the surface is constant with respect to time, the change is with V bar. So I can rewrite this integral to be equals to the surface integral of dou V bar by dou t times ds bar. So if I apply the Stokes theorem right now, I can get that del cross E bar to be equals to minus dou B bar by dou T. Understand that? I have used the Stokes theorem on the left hand side, and from the right hand side, both are, if the integrations are same, then the integrants must be same. Therefore, del cross E bar should be equals to minus dou B bar by dou T. This is the relationship between the magnetic flux density and the electric field intensity. Identify that if the magnetic flux density is not changing with time, then del cross E bar is equals to 0, which is same as what we got for static electric fields. Now, what would happen if a loop is moving in a static magnetic field? So to identify that, you should know that if you have a magnetic field and you have an electric field, this is a magnetic field and this is an electric field. And if you have a charge here, Q, and if you have a charge here, Q, this electric field intensity would exert a force of F is equals to QE on this charge. Whereas the force exerted by the magnetic field intensity on this charge is, that is, magnetic field cannot exert any force on charge at rest. But at the same time, if this charge is moving, let us say with a velocity u bar, then the force exerted by the magnetic field on the charges that are moving is q times u bar cross v bar. Let me write it here, q times u bar cross v bar. That is the force exerted by magnetic field on charges in uniform motion u bar. Now, having the knowledge of this, let us discuss what would happen if a loop is moving in a static magnetic field. When a loop is moving with a constant velocity inside a static magnetic field, then the charges inside the loop are also moving with the same constant velocity. Because if a body is moving, then the every element in the body inherits the velocity. Therefore, charges inside the loop are also moving with the same constant velocity of u bar. Therefore, the force experienced by these charges is F bar is equals to q times u bar cross v bar. Right? Now, if we define a Motional electric field intensity, what is the electric field intensity? Electric field intensity is the force acting on a unit positive charge. Now, if I define a Motional electric field intensity as the force acting on a unit positive charge, which is moving with a constant velocity of u bar, then electric field intensity E bar would be equal to u bar cross v bar. Because, as I have said, E bar is defined, Motional electric field intensity EM bar is defined to be equals to F bar by Q, force acting on a unit positive charge. Therefore, E bar is equals to U bar cross V bar, and if I take the curl of E bar, then that would be equals to curl of U bar cross V bar. So this is the relationship between the magnetic field intensity and the electric field intensity when loop is moving with a constant velocity u bar inside a static magnetic field. If we try to establish the relationship between the electric field intensities and the magnetic field intensities when a loop is moving inside a time varying magnetic field, we do combine the results from earlier two results. Therefore, I get that the curl of electric field intensity to be equals to minus dou v bar by dou t plus del cross u bar cross v bar. See, it has two components. One component is one there is variation in time variation, that is time variation in B bar, and this is when there is time variation in the position of the loop. But the Maxwell has not tried to include this in his result. He wanted to quantify the relationship between the time varying magnetic field and the electric field. Therefore, he has only considered the first component. So the updated Maxwell's equations are that del dot D bar is equal to rho V, that is the divergence of electric flux density is equal to rho V, no change here. And the second Maxwell's equation is that del cross E bar is equals to minus dou V bar by dou T, which says that if there is change in magnetic field or if there is change in flux linkage, then an EMF is produced which opposes the change in flux linkage. So del cross E bar is equal to minus dou V bar by dou T is the updated Maxwell's equation for time varying fields. That is it for today's lecture. In the next component, we would see the updated Maxwell's equation for time varying electric fields and how it would affect the magnetic